Welcome to Saitechinfo channel, my dear students. In today's tutorial, I'll be discussing about Nernst Equation, which is one of the very important concepts in electrochemistry. Let us try to derive this Nernst Equation. A and B are the reactants. C and D are the products. So they involve in a chemical equilibrium, and that is represented by a arrow like this. Here, the progress of the chemical reaction can be represented by change in free energy, particularly decrease in free energy. So according to fundamental laws, one of the fundamental laws of thermodynamics, delta G is equal to, that is, we can introduce minus delta G is equal to minus delta G naught minus RT log J, where the J is the reaction quotient. So, if it is an equilibrium, we can arrive at the reaction quotient or we can also call the chemical equilibrium constant. For example, so as we already mentioned, A plus B gives C plus D. Now, when we calculate the reaction quotient, that is, it involves the product of the active mass of the products divided by the product of the active mass of the reactants. So active mass of the product is here, let us consider C. So active mass of the product C into active mass of the product D divided by active mass of A and active mass of B. See, first of all, you should understand what is active mass. Let me consider that is a sodium chloride solution in a beaker, where the sodium chloride is completely dissolved. Okay, it is uniformly diffused or spread all over the solution. So in that case, the active mass is equal to concentration because it is completely dissolved. So it can be, for instance, that is active mass of what is NaCl, that is nothing but the active ingredients are entirely present in the bulk of the sodium chloride solution. So it can be represented by a square bracket that indicates the concentration of NaCl. But in the case of weak electrolyte, it need not be equal to what? The concentration. So in that case, active mass is proportional to concentration only. So when we remove the proportionality, we introduce the constant, that is, here it is a gamma. So you can put A into gamma C, where this gamma is called the activity coefficient. Now let us not worry about all these things. Anyway, that is, let us consider here being an electrolyte or strong electrolyte, let us consider the active mass is equal to the concentration. Okay, right. So the active mass of C into active mass of D divided by active mass of A into active mass of B, that is given by J. Right. So here we have expanded this J. We have expanded this J as this AC into AD divided by AA AB. Therefore, minus delta G is equal to minus delta G0 and then minus RT into log of AC, etc. Here, according to electrochemistry, the driving force for this chemical energy is obtained from the electrical force. Is it not? Therefore, minus delta G is equal to here N, the number of electrons transferred during the electrochemical reaction. F, Faraday, E, the potential, electrode potential. In the case of cell, it can be called cell EMF. In fact, the Nernst equation is applicable for electrode potential as well as for cell EMF. Now we are proceeding. This NFE, because here on the LHS you have delta G minus delta G. In the previous equation we have minus delta G. So since LHS are equal, RHS must be equal. Okay. Therefore NFE is equal to minus delta G, 0 minus RT log into AC, etc. Okay. So that is what given here. And NF, now let us consider the standard states. So you can put G naught also. So in that case you have to put E naught. E naught means that is EMF or electrode potential in the standard state. And similarly delta G, that is standard free energy change. Okay. So minus, and here we have replaced this GFE according to this equation, based on this equation. So minus delta G 0 can be equated to NFE naught. So minus delta G naught is given as NFE naught, and therefore we have changed this one also. Now we have NFE, is it not? So here we have NFE and here we have NFE naught. So the entire equation can be multiplied by 1 by NF, so that we can remove this NF on the left side. And now once you multiply, the NF can be cancelled, is it not? So NF is cancelled here, and similarly here also cancel, and here minus RT by NF. So we have got this NF divided by NF into log of AC into AD divided by AA AB. And here E is equal to E naught minus RT divided by NF into log of, and this represents the natural log, that is Ln represents Lnx, means log x to the base E, and this is called natural log. Okay. In fact, this is called the Nernst equation, that is this one. This is called Nernst equation. Okay. And these are all the various formats of Nernst equation. For instance, that is we have introduced clearly here E naught. So, and as I already mentioned, we have replaced by the active mass by concentration of C, concentration of D divided by concentration of A into concentration of B. Okay, right. Now E is equal to E naught divided by RT log K, and we know this is called the equilibrium constant. So K is equal to the product of the concentration of the product. What are the products here? C and D, divided by the product of the concentration of the reactant, that is A and B here. Okay, so here it is replaced by K, and E is equal to E naught. Now when you want to, that is, convert natural log to log to the base 10, you have to multiply by 2.303, a factor. Okay, so now you can comfortably call log x. So here it is log, okay, natural log. From natural log we are converted into log to the base 10, and we have introduced the factor. Therefore E is equal to E naught divided by 2.303 into RT divided by NF, and you should know all these expressions. For example, E naught is standard electrode potential. Then R is equal to the universal gas constant, T Kelvin temperature, and N the number of electrons transferred in the half reaction. Then F the Faraday of electricity, is it not? And here K is equal to equilibrium constant for that particular half cell reaction, because we know already for a cell EMF it consists of two half cell reaction. One is cathodic and another is anodic. So we need to consider the half cell reaction, which is nothing but the electrodic reaction. Okay. The same equation, as I already mentioned, can be applied for cell EMF also. In that case, instead of that is E representing electrode potential, you can call it cell EMF, and this is standard cell EMF. Okay, so this is applicable for standard electrode potential as well as for cell EMF. Now let us proceed with some example to calculate the half cell potential. Okay, that is electrode potential. Let us consider an electrode, a metal electrode that undergoes what? Ionization. So it is generally represented as M, N plus. M you can write in the superscript M, N plus. It means that is a metal dipped in its electrolyte. Okay, so that it undergoes a reaction. And what type of reaction is this? Is de-electronation, that is oxidation. Okay, what about reduction? Reduction means it can be represented as M, N plus Ne gives M, that's all. So this is reduction. By Indian convention, we always take the reduction potential only. What about this? This is oxidation. So for oxidation, E is equal to E naught divided by 2.303 RT divided by NF into log of. Now this is the product, Mn plus is the product for the oxidation. Okay, and divided by M. So the active mass or the concentration of any metal can be taken as unity. So in that case, it becomes Mn plus only. So this represents what? That is oxidation potential, because we considered M to Mn plus number of electrons, de-electronation, that is oxidation. Assuming that if it is a reduction, then how to write down? So this can be written as reduction potential. So you can put reduction potential is equal to, so E naught standard reduction potential minus 2.303 RT divided by NF, and put log, and here see that is for this one reduction, so we had to reverse the reaction, is it not? So you can reverse the reaction. So it can be written as electronation, addition of electron is reduction. So Mn plus number of electrons gives M. So in that case, that is log M concentration divided by Mn plus concentration, is it not? And you know very well that is active mass of metal is equal to unity. Therefore E red is equal to reduction potential is equal to E naught reduction standard electrode potential, standard reduction potential minus 2.303 RT divided by NF, and you can put log here 1 by Mn plus concentration. Do you understand? And what about this? This is oxidation potential. But remember that is in India we consider the reduction potential. All the standard electrode potential are represented as reduction potential. Okay. Anyway, now let us proceed. What is the potential of a half cell consisting of zinc electrode in 0.01 molar ZnSO4 solution, zinc sulfate solution at 25 degrees centigrade? So it is given E naught is equal to 0.763. Okay. Now here the half cell zinc electrode. So zinc electrode, let us consider the zinc electrode, zinc Zn plus Zn2 plus 2E, is it not? So the number of electrons involved is 2. So N is equal to 2, remember. And in zinc, and what is the concentration of zinc? ZnSO4 zinc solution is, that is a 0.01. So Zn2 plus concentration is 0.01 molarity. So these are all the given parameters, and T is given as 25 degree So you have to convert this into Kelvin. So 298 Kelvin. Okay. And then what about the E naught value? The E naught value is also given here. So E naught is equal to 0.763 volt. So all these parameters are given. So what you are supposed to do, you have to just substitute in this. Okay. So E, we had to find out this E. Generally, you can represent the potential as E and the cell EMF as E. So in order to distinguish these two for our convenience. Okay. Right. Now let us consider the electrode potential of zinc electrode and E naught value. So the E naught value is given here. How much? That is 0.703. So 0.703 minus 0.059 divided by 2. 2 is the number of electrons transferred. So that we have already indicated. And here log of, what is that? 0.01. So Zn2 plus concentration, 0.01 concentration divided by 1. Okay. So in that case, E naught is equal to 0.703, is it not? So sorry, 763 and minus. So you can divide this. Okay. So 0.059 and you take this log 0.1 value. So what is the log 0.1 value? It can be represented as log 1. Okay, so 2, actually this is 2 bar. Okay, so you can mention this as 2 bar. Okay, so just a minute. Log 0.01 is called 2 bar. Okay, 2 bar. Or you can either way represent this as 0.01 can be represented as 1 into 10 power minus 2, and that 2 bar is given here. Okay, so you can represent like this also, 2 bar. So in that case, 0.059 into log of 0.01 is nothing but, that is minus 2. Okay, so according to logarithm rule, you can bring this as minus 2. So minus 2 divided by 2. I removed the log because I have taken the value. Log 0.01 is nothing but minus 2. So minus 2 minus 2 cancel, and minus of minus plus. So you can put minus of minus plus, 2 can be cancelled. Now you can add 3 plus 9, 2, 6 plus 6, 2, and 1, 7, 8. So 0.8221 volt. So this is the electrode potential of zinc. Okay. So you have to be very careful about this log 0.01. Okay. 0.1 means that can be represented as straight away 2 bar, which is nothing but 10 power, minus 2. So the minus 2 is cancelled here, of minus plus, and 2 can be cancelled. Okay. And you should have some idea about the logarithmic values also to solve this problem. Next, calculation of cell potential or cell EMF. As I already mentioned, this can be represented as a cell EMF also, the same Nernst equation. So E cell EMF is equal to standard cell EMF minus 0.0591 divided by n into logarithmic k. So here Nernst equation, as I already explained, it is applicable to cell EMF. Let us calculate the cell EMF of the cell Zn bar, Zn2 plus, and 0.0001. Then this represents the Saul bridge. Okay, and Ag plus, and then 0.1 m slash, and this one Ag. Okay, so always you must remember on the left side you have got the anode, right side you have got the cathode. Okay. Let us proceed. Since the zinc slash zinc 2 plus, this is anode, at anode oxidation takes place, and what about this cathode? So at cathode reduction occurs. Okay, right. So step 1 cathodic reaction, and the next one is anodic reaction, and the combination of these two is a cell reaction. Okay, and finally you have to obtain the what K value. Now let us proceed. Cathode. So what is the cathode here? Ag plus. So you have got the silver electrode, and it undergoes reduction to give silver, is it not? And this is that is multiplied, actually, that is Ag plus E gives Ag. So this is reduction. And what about anode? Anode undergoes oxidation. So zinc involves Zn2 plus 2E. So remember, that is you have to eliminate the electron when you combine these two equations. So in that case you have to multiply by 2, and that is why we have taken 2Ag. Do you understand? And 2E, then 2Ag, and also the value should be multiplied. So that is 0.80. Okay. So here it was given, you can refer the standard values, and sometimes they will give you. So what about anode? Anode value is 0.76, minus 0.76. Okay. Now what is the cell? You can combine these two. So when you combine these two, you have, that is Zn, then 2Ag plus, and electron can be cancelled since they are in the opposite positions. Then Zn2 plus and 2Ag. Now this is the cell reaction. Okay, this is the cell reaction, and now you are just adding these two values. So 0.6, then 1.56. Okay. So once you are able to establish the cell reaction, and you have to derive the K for that. So K for this equation is the product of the concentration of product divided by the product of the concentration of the reactant, and therefore here Zn2 plus. And you know very well, for silver, that is for any metal, the concentration is taken as unity, so you can ignore. So divided by, and in this case also zinc concentration is ignored. Now you have got Ag2 plus. So Ag2 plus means you can put Ag, not 2 plus, Ag plus 2Ag plus, which is nothing but Ag plus the whole square. Okay. Now so we have this equation here, that is Zn2 plus divided by Ag plus whole square, and that is the K equilibrium constant, and you can substitute here the value. So 1.56, that is the given value, minus 0.059, and the number of electrons transferred is 2 here. Okay. Here we have Zn2 plus, the K value can be substituted, so that you are able to get this. Okay. And finally we can substitute the values of the concentration. So 10 power minus 3 divided by 10 power minus 1, the whole square. So 10 power minus 3 divided by 10 power minus 1. Okay. Ten power minus 3 divided by 10 power minus 1 whole square. So minus 1 whole square means minus 1 into 2 minus 2. So 10 power minus 3 plus 2, that is 10 power minus 1. Therefore log 10 power minus 1, which is nothing but, that is you can apply the power rule also. So if it is minus 1, you can bring this minus 1 here, therefore log 10. So you know the value of log 10, that is 1. So minus 1 into 1, that is minus 1 simply. So here you have minus 1 and minus of minus plus. So 156 plus this much. Now you are able to get the value of the cell EMF. Okay. And try these sums. Zn bar ZnO2 2 minus, then OH minus, and HgO slash Hg. And the next cell is lead sulfate, sulfuric acid, lead sulfate, lead oxide, platinum. And remember that always anode at the left, cathode at the right. Okay. So at anode, oxidation occurs. Oxidation means removal of electron, and here reduction, that is addition of electron. So on combining this, you have to remove the electron in such a way it should be balanced, and finally arrive at the cell reaction, and based on that cell reaction you can get the K. Now you can apply this in your Nernst equation, and then you can get the value of cell EMF. Okay, so this is the procedure, right? And I have given this sample also, example sum. You can just go through that, and if you don't understand you can ask me. Okay, so thank you very much for watching this channel. Please subscribe to Saitechinfo channel to get more educational videos, and you can also ask your doubts in a particular concept. I am ready to that is give the conceptual videos. Okay, please share with your friends. Thank you.